Hello, hello.
Hello. You have to get this part. So 5.
Okay, let's begin, everyone. If you went into the portal and you go into the list of topics, like I said, that's like a book index. So if you have a topic that you want to find where my lecture notes would be, you go into the list index and search for the keyword, and then you would have the corresponding lecture notes, right? So this is the book index where I just copy, highlight it, and copy section 53G, which everyone should have, into the daily summary for this meeting. And let's see, I have the mask. Okay, so the order for today is tall, and we'll see how far we go. I'd like to do section 53F and section 53G. The goal of section 53G is the final result, okay, the complete solution of the coupled equation approach, right? Two coupled equation approach. So that's the, as you see here, the keyword is to obtain the displacement of the problem by relying on the modal displacement, because you can solve for the modal displacement easily. And then there would be some additional qualitative justification and also analytical justification. So the goal here is not just solve for the answer and just leave it there and go home and declare that's finished. You want to verify whether your solution makes sense or not. Okay, so that's what good engineers would do. All right, so let's dive into the subject. And let me. So last time we already started. Actually, I derived the initial modal displacement and talked about the solution of the modal displacement, and already started with section 53F. Solving. We actually did. I already talked about the homogeneous solution, complex conjugate root, the damped circular frequency. I have. Okay, so this sort of halfway here. So let me highlight that part. Okay, and that was from last time. And so for this time, we can just start from there. Okay, so for today, that would be colored in magenta, because that's what we did last time. Okay, so let me bring up section 53F again in two small windows first, so you see the big picture of where we were. Okay, so this is the table of contents, and I have explained the importance of the table of contents because that's the flow chart of everything we did step by step. Okay, so if you missed, you can view the video. I have talked about that before. And on the window on the right, let me scroll down. We have done this. This is an important result here. The modal equation for mode 1 and mode 2. Okay, so these are the two uncoupled, basically two separate problems now. Okay, once you uncoupled the equation of motion, and have the model initial conditions. These are two separate problems. Okay, they no longer couple. And that you know how to solve from differential equation, right? The scalar second order differential equation, and I have the extra lectures, so please make use of that resource. I have the videos also in the extra lectures. Many students have not taken advantage of that resource. And then in the solution for mode 1, right, we reviewed the decomposition into homogeneous problem and particular problem. So this is the homogeneous problem, and this is the particular problem. And down here is the solution for the homogeneous problem, right? The homogeneous solution. And starting with the trial solution. So let me bring up the middle window to zoom in so that you can see better. And we're not going to go through this again, but I just want to draw your attention to the following. So once you replace the trial solution into the homogeneous differential equation and solve for the characteristic equation and obtain the roots, right? The roots here are complex conjugate roots, and like I said, I chose the roots ahead of time and work backward to the at the very top, the original coefficients with all the square roots, okay, because I chose the problem. And so here I also define rho 1 to be minus 1/4, okay, and omega tilde 1 is really 3 square root 7/4. So the definition of rho 1 and omega tilde 1 is already implicit in these two expressions, okay. Likewise, here rho 1 is minus 1/4, and omega tilde 1 is 3 square root of 7 divided by 4. The minus sign is already here. So the two quantities, rho 1 and omega tilde 1, is already implicitly defined in these two expressions, okay? And later on, you need to use these, instead of writing 3 square root 7/4, that's too long, and I use the variable instead, and that's what you see here in the expression, the final, I just want to show the final result, and the final result is right here. Okay, and you see up here, rho 1 and omega tilde 1. Omega tilde 1 is called the damped circular vibration frequency. Okay, the damped circular frequency. It's different from omega 1. Omega 1 is the undamped circular frequency. So there's a difference between omega 1 and omega tilde 1. And if for those of you who are interested, I gave a reference in my lecture summary here. That's this section here. So if you are interested to read further, please do so. I will not go through the details. Okay. In that section 53A for finite element, I have that concept of the damped circular frequency explained. Okay, so so here that's a quick review there, and then by satisfying the initial conditions, right? You find the coefficients Q11 and Q12, and this is the final result, right? Final result, as you see in this expression, there's no more constants to be determined, everything in terms of numbers. You have the exponential with the minus sign, meaning the amplitude would be damped out, so the amplitude would decrease as time goes to infinity. And this is the oscillation, because that represents the underdamped case. The underdamped case, case 3, is the only case where you have oscillation. Right? Critically damped case, there's no oscillation, and overdamped case, there's no oscillation. Okay? So please look at the extra lectures to review. I know many students have not known that, as I talk to some students. And so here, I gave a numerical example to show the difference between the undamped, maybe I should not write over the subscript 1. So omega 1 is the undamped circular frequency, and omega 1 tilde is the damped circular frequency. And this is the relation that I have already explained to you how to remember, you know, in a very easy way. Remember the circle and the radial direction that is rotating. So I have already derived this, and gap T1 is really period. So I said sometimes in many books, capital T is used for period. So gap T1, think of this, and sometimes I use gap T1 in my note. Think of this as P1, the same notation for period, the first period, okay? If you read the book by Crazy, this notation is used. So P1 or gap T1 means the same thing. The first period, or the fundamental period corresponding to mode 1. But the point here is that, you know, if you use the undamped case, then this is the undamped period, and that's pi. And if you look at when you consider damping, with omega tilde 1, which you have seen the number shown in my review earlier, then you can compute the damped frequency, the damped period. So the damped period is a period with the presence of damping. And if you work out the details, because you know the value of omega 1 tilde, that's right here, 3 square root of 7 divided by 4, and 2 pi just because the circle is closed after one period, then that's 1.008. And if you compare to 1.008 pi, right? So it's just a little longer than the undamped period. That's the difference between the damped period and the undamped period, okay? Yeah, that's the comparison is here. All right, so moving forward, and this is the plot using Desmos. You can expect, right, as I keep waving my hands, we have oscillations, and the amplitude of oscillation decreases as time t goes to infinity. This is a concrete plot, which is a representation of what I mean by waving my hands. Okay, and so this is the lower figure is a zoom in, you know, around the initial condition, because you want to verify the initial condition, right? And remember, the initial condition for mode 1 is that the modal displacement is equal to 1 indeed. You know, at time t equals to 0, y1 at time 0 is equal to 1, and the slope y1 prime is equal to 0. Okay, so let me note down here for you. You know, so the value y1 at time 0 is equal to 1, and y1 prime at time 0 is equal to 0, as seen that the slope is horizontal. So you want to graphically verify the result and not just getting the expression and then close the book and go home. Because as an engineer, you may make mistakes, okay? And that's the simplest verification that you need to do. And then, so here is a deeper understanding here. So let me zoom out, so that I have both the plot, the upper plot, and the equation in view. So you see in the graphics, as time goes to infinity, you see that this value here is 1/2, right? So what it says is that the oscillation get die out as time goes to infinity, and the oscillation is oscillating about the value 1/2. So you can see graphically as well as analytically. Analytically, you can also see that by going back to the formula. And so let me erase here. And so this is higher order thinking here, and not memorizing or just relying on the plot. And so here it is. So if you look at the result, right, you see that this term here is multiplied by an exponential with a negative exponent. So, and this term, the term in square brackets, is bounded by, plus or minus 1 multiplied by some coefficients, okay, meaning that it's really just bounded by finite numbers. So when you multiply by this factor, that goes to 0 as time t goes to 0, right? So the first term really will go to 0 as time t goes to infinity. So what is left is 1/2. That's it. That's the proof. That's an analytical proof that the asymptotic value, once the oscillation dies out, is the particular solution. That's why in vibration, keep this in mind. In vibration, the name for the homogeneous solution is called this is the transient solution, meaning that it's just only transient, and in the long term it just disappears. Whereas the particular solution, the physical meaning or physical name is called the steady state solution. Steady state solution. So keep that in mind because that's very physical. So you see there's a mathematical name and there's a physical name. And everything should make sense, and you should be able to go back and forth. And that's it. That's the end of the mode 1. Now we move to mode 2, and the solution process is similar. You have an independent linear second order ODE, and this time homogeneous because I chose not to excite the second mode by design, and then I work backward to the applied force that we see at the beginning of the lecture, of the semester. And the model initial condition now is that we have 0 displacement at time 0, second mode, right? There's a second modal displacement at time 0 is equal to 0, and second modal velocity at time 0 is equal to 1, right? I just make the problem a little more interesting by flipping the numbers, and that is by using the orthogonality properties of the eigenvectors, as you have seen I explained in previous lectures. So the remaining story is similar, except that again by design I want to review for you the case that this is the case where when you solve the characteristic equation, you get the double real root. Okay, so again by design, I want to make mode 1 to be underdamped, so you see oscillation. I want to make mode 2 to be critically damped, okay, where you have double real roots. This is case 2. So essentially, I focus on case 2 and case 3, and by design. So when you have this, so let me go watch you step by step. So when you have this double real root, and the method is variation of parameters or reduction of order, because if you have only one root, right, this is a single root. That's why it's called double real root. Then actually, when you replace lambda equal to -3, okay, into the trial solution, you have only one term. The other term you have to find by variation of parameters or reduction of order. Okay, and the result is that you have the independent variable p multiplied by the first homogeneous solution. So So the two homogeneous solutions here are linearly independent. Okay? But you need two. Why do you need two? Because you have two initial conditions, two model initial conditions. So you need two parameters to satisfy. Okay? If you have only one term, right? If you have only one term, you cannot satisfy two initial conditions. You need to have two terms. And the two functions here has to be independent, linearly independent, meaning that this one cannot be equal to this one multiplied by a constant. That's not independent. All right. So because the factor here is time t, and time t is keep changing. So therefore, these two solutions are linearly independent. All right. So therefore, you have two parameters that you can solve for, and this expression is just replacing omega 2 by 3. That's all. Okay. Omega 2 is equal to 3. So, and note that there's a negative sign on the exponent, means that the amplitude goes down to 0 as time t goes to infinity. Okay. And that's it. This is and so you need to have two equations and for two unknowns. So that's why you need to find the modal velocity, right? And the two, and this is just by taking the derivative of this expression, but we have only two unknowns, P21 and P22, all right? Here, you have both are P22, so it's not like you have an additional unknown. And that's it. And if you replace the two initial conditions for mode 2, right? You have two equations that you can solve for these two unknowns, right? Two parameters, P21 which is 0 and P22 equal to 1. Right? And so the next step is to plot out the results. Express the final result and plot it out. And this is the final result. Okay, the final result is, let me move down a little. It's right here. It has only one simple term, time t times exponential minus 3t, and this is the plot. Okay, and you see that there's no oscillation. This is a critically damped case, no oscillation. The amplitude just dies down to 0 as time t goes to infinity. And zooming into around the origin and plot the slope to verify. Now the scale of the horizontal axis and vertical axis are not the same. So that's why you see that, for example, you can look at, maybe I can move the zoom out, maybe perhaps better. Yeah. So you see. For the horizontal axis, this is 0.1, whereas for the vertical axis, this is 0.1. So that's why you see this line here is supposed to be exactly the bisector. It looks like this, but the slope is 1. Okay? So that verified that initially the mode 2 has modal displacement equal to 0, and the slope, or the modal velocity at time t equal to 0 is 1. See, check. So always check the result and not going away just after obtaining the result. And whether you work in industry or do an exam, that's always a good habit. Okay. Industry is even more critical. You know why? Because you can design things that collapse and kill people. It's more responsibility. Okay, so this is both mode 1 and mode 2 plotted together. And so again, once more, mode 1 you have oscillation, mode 2 no oscillation. Mode 1 is the underdamped case, mode 2 is the critically damped case. That's it. We have completely solved the two uncoupled equations called the modal equation. Now we need to use this result, recombine them, and get the original displacement. That's the goal. You know, that's the goal of the hard work that we did since the beginning of the semester. And this is the final step. Put them together. Critical thinking question, active learning credits. You have my lecture notes. My question is, question is also to excite you to think, right? I mean, if it's just a one-way lecture, it's boring. Like Albert Camus says, right? Lecturers talk, others sleep. So I don't want you to sleep. So I'd like you to participate. How do you make use of the result that you obtain here to find the original displacement? Something that we did before, pointed out to the class. You can look up my lecture notes. You know, this is like an open book quiz, if you like. No penalty, just credits. So active learning credits. Okay. How do you make use of the result that we obtain in terms of the modal displacement and get the original displacement? What is the original displacement? What's the notation for the original displacement? It's really quick. Because once you get that, then you can connect to the two notations together. How did we write the original notation?
Talking about D of T?
Original displacement, Kevin?
D of T, right?
Yes, D1 and D2.
Okay.
Right? So D1 and D2 are the two original displacement of the two masses. This Y1 and Y2 is the abstract displacement in the eigenvector space, okay, relative to the eigenvectors. But this is the physical displacement. This is what you want. Okay, the Y1 and Y2 is the intermediate step. Okay, so how do you obtain D1 and D2 from Y1, Y2? And look into my notes. That's a very critical step. Anderson?
I'm just going to guess that you would multiply by the inverse of the phi bar transpose times the and then inverse of the mass matrix.
You know, okay, let's see, Anderson.
That was a good
You
rep.
remember I did say
Well,
that,
it says that
you know, it's a step after the generalized eigenvalue problem, right? And before projection. And I did say that if you don't have that expression, there's nothing, I mean, the generalized eigenvalue problem would be useless work. That's a very critical step. And what lecture are you looking at, Anderson? Or maybe we can
53,
use-
page 40, or 53E, page 47.
Yeah, projection is the key word. So 53, that should be that should be when you uncouple. Okay, so that's 53E. You see, that's how you think. You need to think that way to find where in the upstream. You know, you need to uncouple the system, and you see, the word projection is key word, and before that, there is something that is very important. Displacement expressed in terms of scalar product of normalized eigenvectors with matrix equation of motion. Yeah, that's the even before that. You know, let's bring up E first and then D. If we don't find in E, then it should be in D. Okay, so let me bring up. This is section E, and yes, so this is still generalized eigenvalue problem. Okay, projection right here. This is the critical steps here. I did mention that. If you don't have this step, there's nothing else to do. You need to express the old displacement or displacement in the old coordinates in terms of displacement in the new coordinates, and the new coordinates are the eigenvectors obtained from solving the generalized eigenvalue problem. This is the expression that you need to use, because now you know y1 and y2. Before, not yet. Now, after solving the model equation, now you know y1 as a function of time t and y2 as a function of time t, and you know the eigenvectors, the normalized eigenvectors. Then this right-hand side here is completely available. All you need is just to plug in the right expression, then you have the solution, right? Which is the displacement that you are looking after. That's it. That's the thought process. Do not memorize. Learn the thought process, and that's what I really would like students to learn more. I provided the best solutions and coach you to do the exam, but I really don't want you to come out of this class and only memorize.
So if you did that, does that tell you where the masses are in the first place before you excite them?
Okay, okay, Kevin said when you did that, does it tell you where the mass is?
So we found y1 and y2. We found the eigenvectors. What is? I mean, I don't get what it gives you. I don't understand.
Okay.
It gives you a displacement. Great.
Yeah, that's you know, in other words, the physical interpretation of this, right? This is what you are after. Physical interpretation of this linear combination. So it has a very beautiful interpretation in the animation that I gave, and the animation went way back to probably 53B. Yeah, right here. Where let's bring up the animation of both modes. Okay. So this is the animation of both modes here. And let me close the code. And so you see this is two modes, mode 1 and mode 2. Essentially, what you see here is the animation of the eigenvectors. Okay, mode 1, keep in mind that it's moving in phase, and mode 2 is out of phase. 180 degrees out of phase. Mode 1 in phase. So that's the physical interpretation. So what is, and so keep in mind that the mode is the same as the normalized eigenvectors. Okay, whereas the modal displacement y1 and y2, think of it as the magnitude, right? So magnitude of mode 1 is y1, and you multiply by mode 1, so that means that how far away, you know, the amplitude of vibration would be for mode 1, and then y2 is the magnitude or the multiplicative factor that you multiply with mode 2 here. Okay, so that's the physical meaning. So let me go back to the expression here. Okay, once more. You know, these two vectors are fixed constant in time. They are not changing in time. Okay, so think of them as whether the two masses are moving together or they are moving opposite each other, and that information is encoded in the eigenvectors. And y1 and y2 would represent the amplitude, how much, you know, more they would move relative to the initial position. It's a very good question, Kevin. I already noted you down. All right, so that's it. That's the plan, and so that allows us to move to section 53G. That's the final section. Okay, and so the final section, that means that we are right here. Okay, you see, we did all of this. Check. Okay, all of these steps are known. You know, we project the equation of motion on the eigenvectors. We uncouple the system into two single degree freedom systems. We obtain the model initial conditions. we obtain the modal applied force, and we solve for the modal displacement. Now we combine the modal displacement or modal coordinates into the final original displacement. Okay? That's what it means. And as I mentioned, that's it, you see? If you had looked into this section, which you have, you would see that I start with this fundamental expression that expressed the original displacement in terms of the modal displacement, right? This is the same expression that you saw when I brought up section 53D. This is section 53G. Okay? So now we have everything. We know the eigenvectors, and we know the expressions for the modal displacement or modal coordinates. All you need is just to plug in the expressions, you know, and that's what is done down here. Okay, so here I do a little more compact. I remind you that this pedestrian expression can be expressed compactly in terms of the matrix variable, you know, gap phi bar and matrix Y. Okay, so where gap phi bar is just putting the two normalized eigenvectors side by side. So this is a 2 by 2 column matrix, and that's right here. You know, this again I have done this many times, and I hope that by now you internalize. This is phi 1 bar and this is phi 2 bar. Okay, 2 columns, right, normalized. And and y1 and y2, so the matrix Y here is right here. Yeah, and so phi bar is the 2 eigenvectors, normalized eigenvectors put side by side, and the column matrix that has the modal displacement 1 and modal displacement 2 as a column is written compactly as the matrix Y. Okay. So in this course, you don't just learn to solve. There are many topics. Okay. Matrix theory, how to go back and forth between equations and matrices. That's part of the topic. Right. You need to be able to do both, because that would lead to the generalized eigenvalue problem, matrix eigenvalue problem. Okay, and so that's it. This is it. This is the final result here. Right? This is just a matter of plugging the different. Maybe let me zoom out so I can show you. Okay. So here. All right. So here. Phi 1 bar is right here. That's the first normalized eigenvector. Y1 is the whole term in parentheses here. Okay, that's the first modal displacement that we already saw. And we saw the expression. These are just copy and paste. What is phi 2 bar? Phi 2 bar is this matrix. Okay, that's phi 2 bar. And what is y2? Y2 is this function t times exponential of minus 3t. That's it. All I did is just put all of the results that we obtained together to have this matrix that contains d1 and d2. These are the displacement of the mass m1 and mass m2 in the original physical coordinates, not the abstract modal coordinates, y1 and y2. See? And so now the next step is to plot, right? Because once you get the result, okay, so here I want to show to you that you can verify analytically that the result satisfy the initial displacement. Why? How? Well, you just replace t equal to 0, right? If you replace t equal to 0, you see that well, the exponential of 0 is 1, right? Cosine of 0 is 1. Sine of 0 is 0. Okay? And then the particular solution 1/2 is right here. Very simple. And for the second term, you see t equal to 0 is give you 0. Okay? So that second term disappears. So what's the end result? Well, what's the end result? That's 1/2 plus 1/2 is 1. And this is phi 1 bar. And you see, that's the initial condition that I selected by design. You know, so to have simple model initial conditions. Okay. So this is really the first normalized eigenvectors. Okay. So we verified analytically that the solution satisfy the initial conditions, the initial displacement. Then you do the same for the initial velocity. Here, before going to the initial verifying the initial velocity, I showed you a clever way, a more clever way instead of the longhand, you know, with all of these terms and numbers. This is a beautiful way to do. Okay. You come back to the expression that give you the displacement, original displacement in terms of the modal displacement y1 and y2, and you just replace t equal to 0, right? T equal to 0 for D, for the matrix D, t equal to 0 for y1, t equal to 0 for y2, and you remember the modal initial condition. y1 at 0 is 1, y2 at 0 is 0, and voila. You get the result immediately without having to go through all of these pedestrian low-level calculations. And so the next step is to check the initial velocity, okay, and oops, yeah, it's okay. I can, you know. And once I showed you this clever method, you can apply the same to the velocity. You no longer need to write all of the detail, because you can, once you take the derivative, then the derivative would only apply to the modal displacement, right? Because only y1 and y2 would be time dependent. The eigenvectors are not time dependent; they are constant matrices. And then you just replace time t by 0, right? T equal to 0, t equal to 0. That's the initial velocity, and you know that y1 prime at 0 was 0, and y2 prime at 0 was 1, and that's it. You immediately get the result is that the initial velocity is the second, was chosen to be the second normalized eigenvector by design. And then this is just the extra step, you know. But you can, in fact, this is the most important step. To obtain this, and this is just, you know, replacing the longhand expression of phi2 bar and just to display it, that's all. All right. And so here is the two, you know, so if you want to plot, you want the expression for D1 and you want the expression for D2 separately, right? So that you can code up in decimals. And that's just, you know, the expression, instead of in matrix form, now you have two scalar functions. And so the next step is just plotting, and this is the plot here. Okay, where you have So D1, that's the displacement for mass 1, mass M1 in red, and D2, the displacement for mass M2 in blue. Yeah, thank you, Casey. And let me zoom out here so you see the bottom plot is just a zoom in, into around the origin so that you can see better. And so in your report problem, please provide plots so that you can explain more the properties of different results. And then there would be more, but let me, it still takes some time to give you a very beautiful interpretation of the result. So let's, I think it's good to stop at this result, right, of the plot of the final result. This is the final result, but not yet verified, in terms of verifying with the initial condition and the physical meaning as time goes to infinity. Okay, so please have the lecture summary. And Michael would have the signature sheet.